Hi, welcome back to our last video in 2.6, combinations of transformations. In this example, we're going to look at a real-life scenario where we can apply some transformation principles to it. So it says, during a race in a sportsman category of drag racing, it is common for cars with different performance potentials to race against each other while using a handicap system. It's kind of like something they use in golf also and other sports as well. So, for example, Byron is racing against Eve. Since Eve has a faster car, when they race, it appears as though Byron gets a head start. The distance E in meters that Eve's car travels is given by E equal to 10t squared, where t is the time in seconds after she starts. The distance B in meters that Byron's car travels is given by B equal to 5 times t plus h squared, where t is the time after Eve starts, and h is the head start. So you can see in this equation, the h there accounts for the head start that Byron is given. On the same set of axes, graph distance versus time for both drivers for h values of 1, 2, 3, and 4 seconds. Okay, so let's begin with that. So we have our two distance equations for both Eve and Byron. So we're going to have to kind of organize this a little bit here. So if we want to graph all their distance versus times, we'll need to write out their equations. So I'll start with Eve. I'll draw hers in black. So we'll put everything in this table here. E of t is equal to 10t squared. And then Byron, we'll go with purple. And we'll do, for the first one, we'll do B1. So that's with a 1 second head start. I'm going to put 1 in for h. So I'm kind of following this equation right here, but I'm putting a head start of 1 second because that's what the question says. So we want to graph his race if he has a 1 second head start, then a 2 second, a 3, and then a 4. So I'm going to put each one in here. So with a 2 second head start, we know that we'll put h in for, so we'll put 2 in for h. Okay, then we'll do the next one in red. And the last one in blue. So a 4 second head start, that's actually quite a big head start. I can't imagine that Eve would win a race, a dragster race, if Byron had a 4 second head start, but we'll go ahead and we'll graph this and we'll see what happens. So let's start with Eve's graph. So that one will be kind of easy. It's kind of just like a parabola, but it's vertically stretched by 10. So instead of doing transformations, I'm actually just going to plot some points. So you can go ahead and copy out this chart. If you need to pause the video, you can do that. I kind of set it up this way just to get everything to fit in nicely. Every square block is 50 in the distance axis, or like the y-axis, and then the x for time. Each one represents 1 second. Okay, so let's start with Eve. So at time 0, so I'm looking up here, if I put 0 in for time, I'm going to have 0 distance, so she's got a point right there. Okay, let's look at 2 second mark. So at 2 second mark, if I put 2 in for t, 2 squared is 4. 4 times 10 is 40. So just below the 50 mark. Plug in 4. 4 squared is 16. 16 times 10 is 160. So that's just a bit over 150. You can see it's growing quite quickly. 6 seconds, 6 squared is 36, so we'd have 360. So it's just above 350. 8 seconds, 8 squared is 64 times 10 is 640. That's going to be way up here somewhere. A little bit too high for us to graph, so which is okay. Let's just try to get a nice graph to go through here. and I'm going to call that E. I'm just going to call it E for this equation right here, E of t. So that's Eve's distance versus time graph. So the way all this graph works is at any time, you could say 6 seconds, you could go up and you could read the distance that she traveled. Okay. The time axis here represents actually Eve's start time. So if Byron gets a head start, that means he's going to be beginning before she starts. So Byron will actually be starting out back here in the negatives. That's why I have this y-axis not at the end of the graph, because we're going to have to plot a few points back here. So you'll see what I'm talking about, a 1 second head start. So we need to plot this purple one first. Okay. So I'm going to do a little bit of mental math again for this one. So once we plot this one, I'm going to use transformations to get all the rest. Okay. So this purple one. So I know that when I look here at time equal to -1, if I put -1 in for t, this will work out to 0, and the whole distance thing will be 0. So at -1 seconds, his distance is 0. Okay. Now, I'd like to get another point at t equal to 2. So I'm going to put 2 in here. So I'm going to have 5 times 2 plus 1 squared. That's 5 times 3 squared. 5 times 9, 45. So that point's going to be a little bit below Eve's time, because we had 40 for that point. Okay, plug in 4 seconds. So this would change to 4. And then we're going to have 5 squared, which is 25. So 5 times 25 is 125. So at 4 seconds, we're at 125. That'll be right there, halfway between 100 and 150. Okay, let's plug in 6. 6 plus 1 squared, that's going to be 5 times 7 squared, which is 5 times 49. So 5 times 50 is 250. We'll have to take 5 off. So 245 we'd be at. 245 is right there, just below 250. Okay, plug in 8. 8 and 1 squared. That's going to be 5 times 9 squared, which is 81. 5 times 80 is 400 plus another 5, so it'll be 405. So at 8 seconds, we're at just over 400, 405. So there we have it. We got Byron's distance versus time. So it's funny, it actually looks like over here he's winning for a bit. Like you can see up here, he's winning a bit, but then Eve kind of passes him like just a little bit after 1 second. So she obviously has a pretty fast car. So this is B1. That's Byron with a 1 second head start. Okay. Now we're going to go ahead. We're going to do the transformations. So this will actually be really easy. I don't have to do any more mental math. I'm just going to erase this little bit of scrap work that we did here. Okay, I'm going to switch over to green because we're now plotting this one. So what's the difference from the purple one to the green one? Is there a way that I can use the purple points to get the green points? So the only difference is we go from 1 to 2 here. So it's kind of like to go from here to here, we're adding 1 on the inside. So it's kind of like having, let's say, an x plus 1 on the inside. So, which we know means a shift left, right? Shift left 1 unit. So that's like the difference to go from here to here, because we're adding 1 on the inside to go from the purple to the green. So it's like shifting 1 over to the left. So that's kind of how I'm going to handle this. I'm going to take all my purple points and I'm going to bump them over 1 to the left. Okay, so I'm gonna neatly kind of draw through here. I know it looks a little bit funny. That's B2. Okay, so you can see that Byron looks like he's ahead in the 2 second race, but then right around here, Eve actually comes through and passes. Okay, so let's do Byron 3 second head start. So I got to move the green graph over one more to the left. So all the points just bump over one more shot to the left. And this time it looks like Byron's kind of winning this part. I kind of drew that last part a little bit poorly. Let me redo that. There we go, B3. Okay. And lastly, this one here. So it's going to have to be shift. It's going to take the red one and it's going to bump over one more to the left. Okay. All right. So those are the graphs for all those. Okay, for both drivers with a 1, 2, 3, and 4 second head start. So this is all part A. Now, the standard length of a drag strip is approximately 400 meters. So I'm now looking at part B. So a typical dragster race is 400 meters. How much of a head start can Eve give Byron and still cross the finish line first? So we want Eve to still win the race. So let's just draw a line at the 400-meter mark. That's right here. This is the finish line. So at 400 meters, you can see with a 4 second head start, Byron will cross at 5 seconds, whereas Eve doesn't cross till about 6.5. The red one, Byron with a 3 second head start, he crosses at 6 seconds, so he still crosses before Eve, that crosses at 6.5. So Eve will still beat Byron with a 2 second head start and a 1 second head start. Eve could probably still win even with a 2.5 second head start, it looks like. If I zoom in, because you can see right here that's a little bit before 6.5. So there's a 2 second head start. If he did 2.5, Eve would still probably win. So it's about 2.5 second head start. So why don't we go ahead? We can answer that. So for part B, I'll answer that up here. We'll say based on the graphs. Based on the graphs, it appears as long as the head start, it appears that as long as the head start is less than, I'll say about 2.5 seconds, Eve will still win the race. Okay. So about 2.5 seconds. Any more of a head start than that, Eve will end up losing the race. Okay, part C, determine the domain and range for each function. Okay, so we want to copy each one of these here. Okay, and just place them down in here in this table. Okay, I'll have to kind of set these up a little bit better. Okay, you can just write them out. You'll probably finish this before I do. Okay. And clean that up a little bit here. Okay, so those are my equations. I want to state the domain and range for them. So if we're going to do the domain and range, I'm kind of thinking the race should only be valid from the time this cars start moving till it finishes the race. So I'll just add that in real quickly here. So we could say for part C, for this situation or context, the equations given are only valid from the time the car starts moving so from the time the car starts moving to when it finishes the race. So we'll say to the time it crosses the finish line. Okay. So if we don't know where the finish line is at, then coming up with the domain can be a little bit tricky. So, or coming up with the time at least could be a little bit tricky too. So, but for Eve, let's go ahead. Let's start with the domain. So we'll say T is the domain. So we'll say T is an element of R. And then we just want to say T is greater than or equal to 0. Okay, so what I could do is I could probably take Eve and kind of see what time she crosses the finish line at, and I could use that for my domain. But we're also not sure what version of Byron she's racing against, so Byron might not finish till a little bit later after that. So we'll just say T greater than 0. The range for Eve, well, she's just traveling a distance of 400 meters. So she starts at the 0 meter mark and then crosses at 400. So we'll use that for the range. We'll say E is an element of R because E is the distance. And E is greater than or equal to and less than or equal to 400. So that would be her range. Okay. This range is actually going to be the same for all the races. So I changed it to B here. Let me rewrite that. B is an element of R, and from 0 to less than or equal to 400. So all the graphs, they all begin on the time axis, so at a position of 0, and they all finish at 400. So that's the range for all of them. So we'll copy that out using those kind of lines there. So that's the range, same for all of them. The time though that each one starts, well, it depends on the head start. Some start at 1 second before Eve, or 2, or 3, or 4. So those times will actually, because they're head starts, they're going to be negative times. So see T greater than or equal to -1. So if Eve starts at time 0 and Byron has a head start, he needs to begin at -1 second. So a 2 second head start, we'll put -2. And then a 3 second, -3. And then lastly, a 4 second head start would be T greater than -4. So that's the domain and range for for all those functions there. Okay, I think we got one more question left, part D. It says acceleration of each car is represented by the stress or compression of each equation. Compare the accelerations of the two cars. So you can see the black curve, which is Eve. It starts off underneath the pink, green, red, and blue graph, but as time goes on, it actually starts to pass some of them. Okay, it would probably eventually pass the red and blue one too later on. So that's because Eve has a faster acceleration. Now, it tells us, it says the acceleration of each car is represented by the stretch of each equation. So looking up here we have a stretch of 10 for Eve. For Byron, it's just a stretch of 5. So we can see their accelerations are definitely different. Eve basically has an acceleration twice the size of Byron. So let's go ahead here. We can write the equation, or why don't we say, sorry, let's write it like this. We'll say A equals to 10 for Eve, and we'll say A equals 5 for Byron. So we could say, therefore, Eve has 2 times more acceleration than Byron. Okay, acceleration is like how fast the speed changes. So her speed increases at twice the rate that Byron's does. Okay. All right, so yeah, that's our last example for this lesson. Hope you find all these videos helpful, and I'll see you